In calculus, solving a differential equation reveals a broad pattern of behavior. While this general solution tells us how a system behaves overall, it yields an infinite family of curves. And to predict one specific outcome, infinite possibilities are too broad to use on their own. This infinite family is the general solution. To find our actual path, we need a specific data point, an initial condition. Pinning a single coordinate creates an initial value problem, eliminating every curve that doesn't pass exactly through that point. That single specific member of the family that remains is our particular solution. Where the differential equation models a general law, the initial condition restricts that law to a single, measurable starting point. Let's put this into practice with a first-order differential equation. We'll start with a scenario where the derivative, f prime of x, is equal to 1 over x squared. Step 1 is finding the general solution. To do that, we take the antiderivative by integrating both sides of the equation. Working through the integration gives us our implicit relationship. F of x equals -1 over x plus c. That capital C is the arbitrary constant of integration. It is the exact mathematical representation of those infinite possibilities we saw earlier. If you forget to write that plus c after integrating, your calculation is stuck in the general form. It is the most common point of failure when trying to find a specific solution. Let's introduce our initial condition, f of 1 equals 0. We plug our x value of 1 and output of 0 into the general solution. Solving the algebra isolates our constant, c equals 1. Dropping 1 back in formulates our particular solution. This chart shows exactly what we just accomplished. Out of all the vertical translations generated by the integration, we found the single distinct curve that successfully passes through the coordinate point 1, 0. By solving for that arbitrary constant, you've taken a broad mathematical concept and narrowed it to an exact model for this specific case. Let's escalate this to a real-world physical application, mapping the exact trajectory of a baseball thrown straight up into the air. The physics dictate our starting point. We know the constant downward acceleration of gravity on the ball is -32 feet per second squared. Because acceleration is the second derivative of position, we are working with a second-order differential equation. That sets our degree of freedom. To isolate a unique solution, we are required to have exactly 2 initial conditions. Fortunately, we have 2 specific data points for this throw, an initial height of 80 feet and an initial velocity of 64 feet per second. Integrating acceleration yields velocity, -32t plus c1. Our initial velocity of 64 makes c1 exactly 64. Next, integrating velocity gives position, -16t squared plus 64t plus c2. Our initial height of 80 makes c2 equal 80, revealing our completed, highly specific position function. Notice the discipline this requires. Multiple integrations increase the variables we have to account for. Strictly segregating your steps and pairing the right initial condition to the matching integration level is the only way to retain accuracy across complex systems. You have successfully taken a generic gravitational constant and built a unique particular solution for this specific throw. So, how do we actually use this new tool? Let's determine the exact moment the ball hits the ground. Hitting the ground simply means the position equals 0. To find the time, we just take our finished equation and set it equal to 0. Solving this quadratic equation yields a positive time of exactly 5 seconds. This graph visually proves our mathematical result. We see the position function track a small dot starting at the 80-foot mark on the y-axis, tracing the parabolic arc, and terminating perfectly at the 5-second mark on the x-axis. Specifying an initial condition is what allows us to extract a single, actionable result from a general mathematical system. Once you can find that particular solution, you can move from describing potential movement to predicting exact impacts. Imagine looking at a completely empty coordinate plane. Your goal is to land exactly on one single, precise point in that space. This animated graph shows what happens when we perform a standard indefinite integration. We get an infinite family of parallel curves. Because we don't know the exact value of the integration constant, which we call plus c, these potential solutions simply float up and down the y-axis, lacking a specific anchor. To lock one specific curve into place, we need an initial condition, a known coordinate on the plane. By forcing our mathematical model to pass through this exact point, we eliminate the infinite alternatives and define exactly one curve. Using this study guide, we follow a strict 4-step framework to find our unique equation. First, we integrate. Second, we substitute our known coordinate. Third, we solve for c. Fourth, we formulate the final specific equation. By applying this algorithm, we transition from mapping theoretical possibilities into calculating exact, concrete mathematical realities. Let's run through this framework using the first example. We start with a polynomial rate function. The derivative is 4x cubed minus 6x squared plus 2. Our initial condition, when x is 1, the function equals 5. Step 1 is integration. Applying the power rule yields our general solution. Pay close attention to this plus c variable. Omitting the integration constant right here is the most frequent cause of calculation errors. Next, we move to substitution. Using our initial coordinate, we replace x with 1, setting the entire equation to 5. Step 3 requires algebraic isolation. The right side simplifies nicely, leaving us with an exact numerical value. C equals 4. Stop here for a moment. It is tempting to solve for c and assume the work is done, but an isolated constant is not a mathematical model. We must complete step 4, the formulation. We substitute the 4 back into our general solution from step 1. This final boxed formula is our particular solution. We have successfully converted a raw rate of change into a specific, unique curve that we can now plot and use for real-world measurements. In physics, finding an object's exact location often requires working backwards from its acceleration. Let's look at this accelerating component. Doing this requires us to run our standard algorithm through 2 consecutive cycles. This problem block outlines our raw data. We have an acceleration function of 6t minus 4. We also have 2 initial conditions, an initial velocity of 3 meters per second and a starting physical position of 10 meters. Let's execute cycle 1. We integrate the acceleration function to get a general velocity equation of 3t squared minus 4t plus c1. Immediately, we substitute our initial velocity, setting t to 0 and the output to 3. Solving the algebra reveals that c1 equals 3. We formulate our unique velocity function by plugging that 3 back into the general equation. Locking down this velocity equation only gets us halfway there. We still need to find physical position, which means we apply the exact same logic for a second round. We begin step 1 again. This equation under part B shows the integral of our new velocity function. This produces our general position function, t cubed minus 2t squared plus 3t plus c2. For step 2, we sub in our physical position condition. At time 0, the position is 10 meters. Because all of our terms containing t drop out, the algebra is immediate. Our final constant is 10. Step 4 is our absolute final formulation. We combine the general position function with our value for c2. We now hold the master position function for this object. By running the integration algorithm sequentially, we stripped away the abstract rates of acceleration and velocity. We are left with a direct tool that calculates the object's exact physical location at any given time. You now have the exact sequence required to take a raw rate of change, combine it with a single coordinate, and build a precise mathematical model. The process relies entirely on this 4-step sequence: integrate, substitute, solve, and formulate. Keep your focus tight. Do not drop the constant in step 1 and explicitly write out the final equation in step 4. As you move forward, practice running this identical framework on more complex trigonometric and exponential rates of change. The steps will never vary. Calculus allows us to map out infinite possibilities, but it is the careful application of an initial condition that lets us track down the one specific truth required to solve the problem in front of us.